Okay, so now we come to the framework for proofs by induction on formulae. So essentially what we want to do is prove that a property holds for any formula x. And so we want to look at the steps we need to take in a form of proof by induction in order to prove that this property holds for any formula x. So the first thing we need to consider is that proofs by induction deal with properties on natural numbers. So we have to figure out how to make a connection between a formula and a natural number. So one thing that we learned in the last class was that the complexity of a formula, which is the number of connectives that a formula has, assigns or connects a natural number to a formula in a unique way. So in order to do a proof by induction on formulae, what we're actually going to do is a proof by induction on the complexity of the formula. And so our framework is going to look very similar to a proof by induction, either simple induction or strong induction, because they're very similar, but you'll see that essentially we're looking at a proof by strong induction form to look at a proof by induction on the complexity of a formula. So we have again two steps, two cases. The first is the basis step or the basis case. We need to prove that the property P holds for all atomic formulae x. In this case, we're considering that the complexity of our formula x is 0. So any atomic formulae is defined to be a formula of complexity 0, has no connectives. So we prove that our property holds for all atomic formulae, all formulae with complexity 0. Then the induction step, again, first involves an induction hypothesis. So in this case, we assume that our property holds for all formulae with complexity k strictly less than n, where n is the complexity of our formula x that we want to prove has the property. So in this case, we can see that it is of the form of strong induction because we're assuming the stronger induction hypothesis that the property holds for all formula of complexity k strictly less than n, not just of complexity n minus 1, for example. And now we want to prove that the property holds for x. What does x look like? So we know at this step that it has complexity 1 or more. So that means that it has at least one connective, so it can have one of two forms. The first possible form it can have is that it is of the form not A for some well-formed formula A. In this case, if x has this form, we need to show that the property holds for a formula of this form. But notice that in this case, since we assume that x has complexity n, then our formula A has complexity n minus 1. It has one less connective than x, since x has a complexity of A plus 1, since we're adding just one connective to A to get x. So that means that we can apply our induction hypothesis to A because A has complexity n minus 1, which is of complexity strictly less than n. So we know that the property holds for A, and we use this to show that the property holds for x, which has the form not A. However, we have another case. X could have the form A circle B, where circle is any of these binary connectives, and or implication or equivalence. So again, notice that A and B, the formulas, the well-formed formula that make up x, have complexity strictly less than n. We know that in fact the complexity of x is equal to the complexity of A plus the complexity of B plus 1. So each of these formulae A and B have complexity strictly less than n. We don't know exactly what their value is, which is why we need the stronger hypothesis, but essentially we can assume by the induction hypothesis that the property holds for A and B, and we use this to prove that the property holds for x, which is of the form either A and B, A or B, A implies B, or A equivalent to B. And this is all possible cases of the form that x could have based on our formula calculation. And so this ends our framework for proofs by induction on formulae. So as long as we follow all of these steps, we have completed a proof by induction on formulae. We'll see in class how to prove some of these meta-theorems, right? So remember, a meta-theorem is a theorem from outside of logic. In the meta-theory, proving properties of logic or properties of well-formed formula. So we can prove using induction on formulae that every Boolean formula A has the same number of left and right brackets. So this is a property of formulae, so it is considered a meta-theorem. We can also prove any non-empty proper prefix of a Boolean formula A has more left than right brackets. Again, we can prove this by induction on formulae. And in fact, we won't prove either this corollary or this theorem in class, but you can look at the proofs in the textbook. All right.